can significantly impact the output of solar panels. And of course, this is related to the last lecture because we were talking about scattering in the atmosphere. Pollution is of course much more recent, but I would encourage you to go read it. This is just a press article, so this is interesting. You can just read through it. It gives you a feeling for what we are learning has real world implications. I mean, this basically what they're showing is that it could have it's a pretty short article, so you can read it. They're showing is that they actually did the analysis for Delhi in India, which is a very polluted city. And they showed that you can have basically a loss of several, maybe tens of millions of dollars every year, just from the fact that you are reducing the amount of sunlight that reaches the solar panels. And this is not a very simple calculation, so it's kind of interesting to actually look at it and how this relates to. And it was serendipitous that this just came out like 2 days ago, and we just talked about it, right? This basic exact same thing to some extent. So and if there's some interesting things like that, I will post it here and I'll let you know. So I would encourage you to read it because it will allow you to kind of put into context what you're thinking about in the class. And if there might be things that I miss in the class, we'll kind of emphasize. So this is an opportunity to kind of, okay, something's happening in the world. Let's kind of think about it. Okay, so that's there. The other, of course, important announcement is the project teams and assignment 1. So the teams have been assigned, and the instructions for assignment 1 are posted here. So we can look at that, but the most important thing, make sure you identify your team members today and come up with a plan to meet and so on. So we'll talk a little bit about that in today's lecture, but if you click on the PDF here, you can figure out all the instructions. We'll go through it again shortly, okay? But before we do that, I just want to keep in mind where we are on the schedule. So today we are going to cover basic thermodynamics. This is very, very kind of a big picture overview, just looking at kind of very high level. And the idea is that we want to understand enough to start thinking critically about our projects. Okay, what do I need to understand in terms of improving the performance of whatever the particular problem that my team is trying to solve? This is really my goal here. It's pretty likely that you probably won't have anything directly related to this in your exam. So, of course, the concepts are important, so there might be questions related to the concepts, but I'm not going to ask anything specific to thermodynamics. That's it. Okay, so having said that, let's, oh, and yeah, so I'll come back to the rest of the schedule later on, so let's just jump right in to the team assignment. So I want to spend I want to spend a few minutes talking about the assignments and projects because, of course, this is a very important part of the class. Again, as I mentioned in the first lecture, my goal really is for you to experience what it would be like to work in small teams in a real-world company. So imagine yourself in a company or in a startup trying to innovate and understand the problem that you're trying to solve. Of course, in the first assignment, you're going to identify the problem you're trying to solve, but really that's the experience I want to bring to this class. So keep that in mind. So we have 5 in-class teams, 3 students per team and 1 online team, 2 students in that team. So your presentations, of course, please limit to about 10 minutes with a Q&A of approximately 5 minutes. So keep that in mind, roughly 15 minutes. That gives us, 5 times 15, 75 minutes, plus some margin. So we can do this during the class. Okay, so I tried to account for all your preferences, whoever emailed me, so you can see your team here. So make sure I would say at this moment, identify which team you're with and kind of introduce yourself to your teammates. And of course, most likely these are people you've never met before. So do that now if they are here. I mean, you don't need to. I mean, you can do this yourself. So just make sure you identify who you're working with. Okay, so Evan, Dalin, and Dongbun on solar daylighting, Yang, Dan, and Joseph on solar water desalination or pasteurization. So, by the way, these are very broad suggestions. So, I would suggest and encourage you to take the topics in any direction that your team prefers. Okay? And I will also add that if you have any problems with the topics assigned to you, for instance, you're not excited about doing something, so let's say Evan is not excited about daylighting, he can just, or, I think you have to come up with a plan like a team and email me. Okay, we want to do something else. Yeah, I'm very flexible from that point of view. The most important thing is I want you to be excited about the topic. Okay. All right, so solar refrigeration / cooling, again, it's very broad. Take it in whatever direction you like. Michael, Gavin, and Nathan. Concentrated solar. Here, I'll give you an example here, what I mean, but really photovoltaics, thermal, or hybrid systems. Hybrid systems are very interesting. I can, of course, in any of these topics, if you are stuck or if you have questions, just email me. I'm more than happy to share information, share my insights and things like that, whatever I know. So this team is Aaron, Jeffrey, and DJ. And solar cooking processing, again, I kind of left it fairly broad, so you can take it in whatever direction. Stirling, David, and Jake. The online team is going to work on concentrated solar because that's kind of the focus of the class anyway. So that'll be Aaron and Daniel. So first of all, is everything? I'm going to stop for a few seconds and see if there are any questions at this moment. Or okay, that is silence. So I assume there are no questions. Again, if you are unhappy about any of this, just email me. It's hard to change teams, but we can consider changing topics, that's for sure. Okay. Can I move on up with them? No questions? Okay, good. So let's, actually, before I go through the examples, let's go look at this. So the first presentation will be in class on September 13th, like I said, about 10 minutes, okay? So this is your homework, really. Number one, pick a team name, okay, that allows you to identify yourself. Number two, select a time to meet regularly as a team. And this could be remote, like you can just do it on Canvas. It doesn't need to be in person. I know everyone's busy, so you can use Canvas chat or forums or it's important to have kind of a regular time to meet because all of you have classes and schedules, so kind of pencil it in. So you are forced to meet and kind of think about these things. Otherwise, you'll end up at the last minute and the output won't be very good. And you won't get enough out of the class. So it's important that you do this. Number three is what you have to do for your first presentation. So again, you don't need to submit a report. All you need to do is prepare a presentation and present it in class. Okay? The online team will be doing a video, but that's different. So what you need to do first is to review current solutions in your project topic. Like I said, you have to first decide what your project topic is. I gave you broad guidelines. You're welcome to keep it broad, or at this point anyway, you can either keep it broad or you can start going narrower. So for instance, for the solar daylighting team, you could say, okay, I want to look at daylighting with fiber optics. That's the only thing I want to look at. So that's a narrow focus, but that's fine. You can start there. So the goal there would be to review current solutions in your current project topic, so to understand what the landscape is as it exists today. Next, I want you to discuss the pros and most importantly, the cons of the current solutions. I want you to identify what are the main advantages of the current solutions and really why people actually use it, right? Why is a customer using that solution? And if you can, more importantly, identify the problems, the cons, the disadvantages of the current solution. And of course, you don't have a lot of time, so it has to be brief. So the whole thing has to be 10 minutes, right? And from this analysis, I want you to identify the main problems, I would say main top 3 problems that you want to solve in your project topic. Okay? And the reason to identify the main problems is because those are the main problems you will address in your next assignment, which is how do you solve those problems. At this point in time, you don't need to worry about how to solve the problems, just identify the problems. I mean, of course, if you can think about how to solve the problem, that's also good, okay? But at this point, your main goal is to identify the problems. Okay, so you really have about 2 weeks or a little bit less, so it's not a lot of time. So I would recommend starting on this right away. Okay, so what I want to do next is I want to kind of go through a few examples of some projects ideas. I've given you a lot of ideas, but I want to go through a few examples here before we dive into the thermodynamics lecture. And the reason is also, again, because these topics that I threw at you are very broad, kind of vague. I want you to start seeing some concrete things. By the way, it doesn't mean that these ideas are exactly what you need to work on. It just seeds for you to think about. Okay? Think along those things. Okay, so I'm gonna go and see if this is. Oops. Go back. Okay, is everyone okay with the instructions for the assignment? Okay, if you have any questions, you can just email me, of course. Okay, so this is a very simple example of water. So again, the question I'm asking this is obviously for the desalination team, is can you make a simple, cheap, portable water desalination pasteurization system? Yeah, that would be a very, very useful thing to do. So let's see an example here. Hopefully it'll play. I'm going to pause it, and first, Apratam, can you hear the sound of the video? Yeah. Okay, let me try disconnecting this for a second.
Simple, very primitive desalination facility that can be.
Okay, I think just for the video, I'll turn this off.
Once again, we're continuing in the solar village, and here's an example of a very simple, very primitive desalination facility that can be used to remove salt from like ocean water or seawater, and also to clean the dirty water. And this is completely free except for the cost of the actual equipment. So basically what you have inside is black surface. You pour salt water inside and you have this glass dome, this glass pyramid. So what happens? The solar heat evaporates the water goes up and it ends up on this glass, and then it drips down, comes here, and is collected here. So now you can drink that water, it's pure. And basically this, it's a little bit more than a square meter, but you can get about 10 liters of pure water from this thing per day. 10 liters from this here. So 10 liters is basically enough for one person for one day. So this is a very clean and efficient way, but the problem with it, it uses a lot of space to create a lot of water, which can affect the environment. So that's always the argument for building these massive facilities of evaporating and cleaning the water this way. Now, a lot of water desalination actually uses energy, fossil fuels, and it can produce a lot more water in a much smaller space. So that's what's being done in Israel. Actually, now Israel produces 60% of its fresh water from seawater, but it uses a lot of energy. And this is completely energy free because it uses solar heat to produce water. And on small scale,
I think this is the best from the environmental perspective, but once again, if you need a lot of fresh water, you would use a lot of space, and actually, this is very cheap to build, but once again, if you use a lot of space, it can affect the environment. So, alright, this was Leo.
Okay, so you kind of see a couple of things here. First of all, you see that he identified a problem, right, in terms of space and the amount of water. So that's an example of a problem in this space that you can try to solve. In fact, probably the most important problem for desalination. But you get an idea. There was something else I was going to say, but I kind of slipped my train of thought. But anyway, let's keep going. So that's an example. Again, a simple example. So from an optics point of view, you can think about, okay, well, can I redesign this in different ways and so on, right? Anyway, so that's the innovation part of it, which you will work on in for the next assignment. Okay, so that's one. Whoops. Okay, so two of the teams have what I refer to as concentrated solar, or I call it photovoltaics and thermal or hybrid system. So it's basically a system that can produce electricity, which is what photovoltaics does, and heat. Okay. So again, the question is, can you design a system that's inexpensive, portable, and has high efficiency? So let's think about, let's look at an example here. So this is obviously from a company, and this 10x refers to concentration of sunlight, as you will see. So they're using a parabolic trough with water passing through the focus of the parabola. We saw this before, we'll see this again. This will become a very recurring theme in this class. And you can see the tracking here. There's a motor to rotate the parabola. Yeah, as you can see in this cartoon, right? And the 10x refers to the fact that there's an increase in concentration by a factor of 10. We'll talk about what that is when we talk about non-imaging optics in 2 weeks. So they're passing cold water through, right? And it gets heated up. So you can see as the power increases, the temperature, one side increases, the other side, Well, so in this case, it's a hybrid system. It's not shown obviously, but so before I go into that, they can make it modular, so they can plug and play. I suppose that's what they're claiming. In this case, the water could be purified. In this case, they could use the heated water to run a turbine, or they could use the water to just heat a room or a building or something like that. So that's an example of hybrid thermal and photovoltaic. Now, of course, what I should have really shown is a system where, where you have a solar panel, which is basically then cooled by water going underneath it, let's say, because the cooling a solar panel always usually improves its efficiency. So that's an example where you can produce electricity from the solar panel, but at the same time produce heat from the solar panel as well by just cooling the solar panel with water. But in any case, those are examples of things that those teams can actually think about. And when you do your literature study, you will see a lot more other examples as well. Let's see. Whoops. So here's another example of a solar refrigeration / cooling capability. Again, the question is, can you design a simple, cheap, portable, cheap refrigeration system? So very, very recurring theme again here. So let's look at the video. So again, this is from a company called Sophagy, and I think there is narration. So
I'm Zaina, the corporate communications specialist here at Sophagy, where we're creating simple solar technology solutions for commercial, industrial, and utility clients. In this episode of Sopo How, I'll explain how our micro CSP parabolic trough technology is used to create solar air conditioning.
Okay, so we kind
In
of
solar
see,
air
yeah.
conditioning, a set of Sopage micro CSP Sopanova troughs are connected to a thermally activated chiller running on heat. Different types of thermally activated chillers are absorption, adsorption, or desiccant systems. Adsorption and desiccant chillers are less common, so we'll focus on the absorption chiller principle. In these systems, water, the refrigerant, absorbs heat at a low temperature and low pressure during evaporation and releases heat at a high temperature and high pressure during condensation. Lithium bromide solution, which acts as the absorbent, is used to absorb the vaporized refrigerant. The evaporation of the refrigerant takes place at a low pressure. The diluted solution, which contains the absorbed refrigerant vapor, is heated at a higher pressure. As lithium bromide becomes dilute, it loses its capacity to absorb water vapor. It therefore needs to be reconcentrated using a heat source. This leads to the vaporization of the refrigerant, and thus the solution is restored to its original concentration. The cycle keeps repeating itself to give the desired chilling effect.
So this is exactly as what we had discussed before. Just to point out, remember there's a hot part and a cold part, and there's condensation of the cold part, which is here, and then there's essentially evaporation of the hot part. Right, so it's exactly like the normal refrigerator that we've seen before. So, okay, let's come back and continue here.
Absorption chiller system efficiencies are often around 0.7 COP, or coefficient of performance, for a single effect, or 1.2 for a double effect absorption chiller, making for a good complement to the efficient Sopage micro CSP solar collector.
Yeah, we won't use these.
Sopanova is the ideal technology for solar air conditioning because of its unique sun tracker, which gives the system higher production and storage, allowing for consistent and reliable operation.
Yeah, so
as demonstrated in this graph, solar air conditioning is an ideal renewable energy solution as there is a direct correlation between solar radiation and cooling load demand. The red line signifies the available solar radiation on a typical summer day, the blue line signifies a typical building cooling load, and the green line signifies a typical cooling load harnessed from solar energy. When the sun is at peak radiation, the demand for air conditioning is at its highest. Likewise, this is when solar cooling is also at its highest, as it is using thermal energy to directly drive the solar AC system. This makes solar air conditioning an ideal solution for our customers. Remember, every customer's need is different, so please visit us at www.
yeah, so again, the idea there's a hot part and the cold part. In this case, the hot part is created by heating the water or the fluid with solar concentrator. So it could be something similar, or it could be even simpler. It could just be even a simple evaporative cooler, something we're used to in Utah. So something.
Dr. Menon, your volume went down.
Oh yeah. Okay. Yeah. I'll. I think 1 second. So is this better? Can you hear me? Yeah. So moving on to the next topic, I'll just give you, I think, one more example of the solar daylighting. There are, of course, several commercial solutions, and just picked one as an example. Again, for the daylighting application, you can think about, how do you make it more modular? How can you integrate it with HVAC or these fibers, etc. So let's take a quick look at the solution, and then we'll move on.
Good morning, my name is Frank Harrington, I'm from Solar Cube Australia. Today we're presenting you our 750DS daylighting product. It's a tubular daylighting device. We can deliver light from a roof line up to 15 metres away through a ceiling cavity. We use our Spectralite Infinity to enable us to do this. It has a 99.7% reflectivity. We also employ our Raybender 3000 technology on the dome to capture the maximum amount of light that we can during the day. This here is our dome, which uses the Raybender 3000 technology. It captures a lot more early morning, late afternoon daylight than traditional daylighting technologies. We also incorporate with that the tubing, which has a
this video is very choppy.
99.7%.
Okay, well, it's almost over, so I'll post a link to it. I'm going to stop here, so if it's too choppy, but So you can see what happens is that, this is the output of the light. They are doing two things. One is that they can make it more uniform. They can homogenize it. At the same time, in the beginning, they showed this dome here, which allows you to collect more light. So it's kind of like a collector, not really a concentrator, but there's no tracking that happens here, obviously. So that's just another example, and yeah, so you can take a look at that. So there's a website. It's an interesting technology. I think so. The last one. Can you still hear me, Pratham? Can you hear me okay? Yeah. So the last one I want to show is a topic that we haven't actually talked about, and I haven't assigned to any team, but we will actually talk about it later on. Is basically how do you apply optics in recycling? How do you sort recyclables? And this turns out to be a very important problem. So we'll take a quick look at the example here, which shows recycling at very, very large volumes and at very high speeds is enabled primarily by fairly complicated optics, and there's certainly a lot of innovation that can happen in this field. But this is just showing an example of one of these huge machines that do recycling. So for instance, in Salt Lake, it's something like this. Let me see if I can show. So it should show some materials flying through on a conveyor belt. So you get a sense for what is happening. Yeah, so there you go. So there's a whole variety of materials essentially flying through a conveyor belt, and you need to have a very, very fast size and shape recognition system, which is of course a camera and some very fancy software which allow you to essentially separate out this material. But you can see the amount of speed that goes through it. Of course, it's also used in classifying agricultural products and whatnot. In this case, they're showing beans. But the same technology is applied also for sorting recyclable materials, which we'll talk about later on. But yeah, the impressive part here is the speed, right? They have to do these things really, really, really fast. Okay, so anyway, so that's an example of where optics could play a big role in the recycling industry as well. Okay, so basically this is where I want to stop talking about. Can you hear me? Yeah, sorry. Yeah, so I think you have an idea of, some ideas about different problems in different topics, and I'd like you to start. Applications. Okay, so let's move on to Are there any questions? Okay, so the level of thermodynamics that we need to understand for this class is fairly large, high level. So we will only cover it at a high scale. So first, we need to understand what a heat engine is, and we have actually seen this several times already in this class. The heat engine is basically a system that converts heat into work, and generally this could be heat coming from light, or it could be fuel. And the idea is that whatever heat is generated is then applied to do work, and this could be motion or it could even be electricity. So keep in mind, when we say work in thermodynamics, that doesn't necessarily mean mechanical work. It could also be electrical work. Okay, as we all know, motor is doing electrical to mechanical. So this is probably the simplest form, one of the simplest forms of a heat engine, where you have a hot area. In this case, heating water. So it's a temperature T1. It evaporates, becomes touches a cold area, okay, up here at a temperature T2, and then it pushes a piston. Okay, this expanding steam pushes a piston, which turns a wheel. So that's the work output is the moving wheel. The heat input is the input. Okay, And of course, we can define this entire system here as a closed system and define laws of thermodynamics around it, which is exactly what we do. So the key concepts to understand are the heat difference is used to generate electricity or generate energy. Okay, this is, again, we've seen this several times. I will repeat it until it becomes intuition. Then the examples, of course, are coal plants, nuclear power plants, solar thermal plants, geothermal plants, also thermoelectric devices like the Peltier device that we saw in the last lecture. Okay. Another simple example that all of us are familiar with is the internal combustion engine. So this is a very simple model of an internal combustion engine with a 4-stroke type cycle. So the system consists of basically a chamber here. It's called a combustion chamber. Okay. First, there is an input valve through which air-fuel mixture comes in. Okay. There's a spark plug which initiates an explosion, as we'll see soon. And there's an exhaust valve which is close to the very beginning during intake. So first, there's the air-fuel mixture comes in, which pushes the piston down. Okay. This piston is connected to this crankshaft, which turns the wheel, okay, axle. So first, you have the air-fuel mixture drawn in, so everything is drawn in. So it's rotating in that direction. The valves are then closed, okay, and there's compression. So it continues rotating, okay. So this chamber is now compressed, so high pressure, low volume, and we'll come to a pressure volume curve soon, so keep that in mind. Air-fuel mixture is compressed. There's a lot of potential energy there. And then the spark plug fires, which creates a chemical reaction, which is explosion, which creates products at a very, very high pressure. So they have to expand, right? So the explosion expands the gas and pushes the piston down, which forces this to rotate again. Okay, and the last part of the cycle, basically as it rotates, the exhaust valve is opened and the exhaust gases are pushed out. And the cycle repeats again. Okay. Again, this is an example. This internal combustion engine is something we're very familiar with, but it's an example of a heat engine. A heat engine can be thought of in a very general form, internal combustion engine. Of course, in academics, we will think about this from a very theoretical point of view, which is why we're talking about heat engines. So you can have various different kinds of conversions of energy. You can have light being converted to electricity, which is of course photovoltaic effect. You can have light being converted to fuel, which is something like fuel cells or solar fuel generation. Of course, in nature, that's photosynthesis, right? Or you can have fuel to motion, and again, that's it. All those are different kinds of heat engines, essentially energy conversion systems. Photovoltaics, photosynthesis, biofuels, hydro, wind, tidal, etc. Now, for us, from a practical point of view, we need to know what the efficiencies are, because this really drives the cost and adoption, right, use of these technologies. So electric generators generally can be quite efficient. This is mechanical to electrical, greater than 80% efficiency. Electric motors are the opposite. Electrical to mechanical generally can also be very efficient, greater than 90% efficiency. Of course, this depends on, we talked about this before, this depends a little bit on how it's used. So, for instance, if this motor is running at variable speeds, then this efficiency drops quite fast. But if this very high efficiencies can be achieved if you're always at a constant speed, rotational speed in this particular case. You can have light to heat, which can have 90% efficiency, which is concentrated solar thermal systems. You can also have chemical to heat, which is of course burning fuel, which can also be 90% efficient. Of course, the problem with chemical to heat is that you usually end up with toxic side byproducts, which can pollute the environment. So we need to consider those things as well. Now, in heat engines, the most important thing to keep in mind is the fact that there are limiting efficiencies. So there are theoretical limits to what efficiencies can be achieved. And in thermodynamics, places the upper limits on these efficiencies. Okay? So of course, we want these efficiencies to be as high as possible, but the thermodynamic limits limits what we can achieve, which means that we need to understand what those limits are, so we can understand, okay, how well is our system performing. So thermodynamic limits for a heat to mechanical system is defined by what's called a Carnot limit. We'll see this again, but just to, this equation is simply 1 minus the temperature of the cold part divided by the temperature of the hot part. So these are heat engines, solar thermal systems, and so on. So from this expression, you can see that if the temperature of the cold part and the hot part are the same, then it becomes 1 minus 1, it becomes 0. So it's not producing any energy. But if the temperature of the cold part is very small, temperature of the hot part is very high, then this number here goes to very small values, which means that you're getting close to 1 or 100% efficiency. So you really want to make the cold part very cold, hot part very hot to get this efficiency to be high. Okay, but of course there are problems with that, as we will see later on. Light to electrical energy is, of course, photovoltaics. Again, just keep in mind that even in photovoltaics, the limit, the thermodynamic limit is still defined by that. Of course, in that case, the hot part would be the sun, because light's coming from the sun. The cold part will be the temperature, the ambient temperature at which the solar cell is. We'll also talk about that later on. Light to fuel is a similar situation. Of course, it's much slower as photosynthesis. The efficiencies are generally a little bit lower as well. Okay, so the basic principles are enshrined in basically 2 laws, which we call the first law of thermodynamics, which is essentially an energy conservation law, and then the second law of thermodynamics, which talks about entropy. Okay, so the first law of thermodynamics is stated mathematically as delta U equals Q minus W. Now delta U, so here we're talking about a closed system, a system where there is no, there are boundaries, so no matter can go in and out. Now energy can come, or heat can come in and out, but not matter. So delta U refers to change in the internal energy, and we'll talk about what that internal energy means in the next few slides. But the change in the internal energy of the system is balanced by the amount of heat added to the system, which is Q, minus the work done by the system, which is W. Okay, and that's a very fundamental thing. If you think about it, it's basically conservation of energy. Okay, so let's think a little bit more detail about it. The first law of thermodynamics refers to the increase in the internal energy of a closed system. So closed system is important because it means that the system is not allowing material or matter to go in and out, is equal to the total of the energy added to the system, okay, minus work done by the system. So the net energy added to the system. So specifically, the energy entering the system is supplied as heat, and if energy leaves the system as work, which is generally the case in most heat engines, the heat is accounted for as positive, so this Q is considered as a positive number, and the work is negative, which is why you have a negative sign here. So heat minus work done is the internal energy of the system. Okay, so that's relatively straightforward. Now, of course, these closed systems are not static. They're because they are receiving heat from the outside and they're doing work, which means that something is happening, right? They're not just sitting still, like the internal combustion engine, for instance, right? It's moving. So there is some cycle happening, and we refer to this as a thermodynamic cycle. So in the case of a thermodynamic cycle of a closed system, which returns to its original state, just like the internal combustion engine comes back to its original state, so it's a cycle, the heat Q in supplied to the system in one stage of the cycle minus the heat Q out removed from it in another stage of the cycle plus the work added to the system W in equals the work that leaves the system W out. It's basically restating this equation. Okay, so in other words, the change in the internal energy of a system during a full cycle, and we'll see what that means with some examples shortly. It really means that it goes through into a cycle. It means that the initial state and the final state of the cycle are the same, which means that the change in internal energy of the system is 0. Therefore, the heat entering the cycle minus heat leaving the cycle plus work being done on the cycle, on the system, minus the work done by the system should all match. It should cancel out. Okay, QE equals W net. This equals 0 in a cycle, because you're starting at the same state and ending up at the same state. So we can go to a very specific case. In the particular case of a thermally isolated system, which is also referred to as adiabatically isolated. We'll come back to what adiabatically isolated means. But let's imagine a situation where it's completely thermally isolated from the outside. In other words, no heat can come in, so Q is 0. The change of internal energy of an adiabatically isolated system can only be the result of the work added to the system, because of the adiabatic assumption is Q equals 0. So if Q equals 0, then delta U of the system is U final, internal energy at the end, minus U initial, which is internal energy at the beginning, is W in minus W out. So that's a thermally isolated system. So if you have a completely thermally isolated system. These distinctions are important in different situations, so we'll look at some examples. But there's quite a lot of abstract concepts here, but most important things are somewhat common sense. So let's try to distill them out. What are the key ideas from a conceptual understanding? Number one, of course, is conservation of energy. Energy put into the system, energy taken out of the system should match whatever change in the internal energy of the system. The second, so that's pretty simple. The second concept is this concept of internal energy. We haven't talked too much about it, and it's not very easy for most people to appreciate. So let's take a quick, closer look at this. Okay, really, the internal energy refers to energy of the constituent components of a system, which could be molecules forming, a material. It could be, planets moving around in a solar system. So if you think the solar system as a system, as a heat system, let's say. So it really depends on how you define the system. So let's take a look at how it's defined. If the system has a definite temperature, then its total energy has 3 distinguishable components. Okay, so energy, of course, can be in motion. If the system is in motion as a whole, it has kinetic energy. We know that. If the system as a whole is in an externally imposed force field, let's say like gravity, then it has or it could also be electrostatic potential, right? Like this force field could be not only gravity, but it could also be, for instance, in a photovoltaic cell or a solar cell, you have the electric field, right? Could be an electric field. So any of that can result in potential energy relative to some reference point in space. And thirdly, it has internal energy. Internal energy is a fundamental quantity of thermodynamics, and it really establishes the difference between work done into the system and work done by the system, or heat input into the system, work done by the system. So the establishment of the concept of internal energy distinguishes the first law of thermodynamics from the more general law of conservation of energy. So the E total of the system is the kinetic energy of the system plus the potential energy of the system plus the internal energy of the system. So again, from a microscopic point of view, the internal energy of a substance can be explained as the sum of the diverse kinetic energies of the erratic microscopic motions of its constituent atoms, which is what I was saying before, and of the potential energy of the interactions between them. So it could be the air molecules, right, moving around. So if you have a chamber filled with air, the internal energy of the system is simply the kinetic energy of the air molecules within that system, within that chamber, and any collisions, right, potential energy resulting from the collisions. So those microscopic energy terms are collectively called the substance's internal energy, or U, and are accounted for by macroscopic thermodynamic properties. So of course we won't go into that level of detail. We will essentially abstract it out. The total of the kinetic energies or microscopic motions of the constituent atoms increases as the system's temperature increases. So we know as things get hot, they start moving more. So kinetic energy of those microscopic motions increases. We'll see that again, but just keep that in mind. This assumes no other interactions at the microscopic level of the system, such as chemical reactions, potential energy, or constituent atoms with respect to each other. Okay, so it's a bit abstract, not terribly important for us to know in great detail, but you need to understand conceptually what, that there is something like something called an internal energy and how it relates to work done by a system and heat input into a system. Now, work done by a system is the other concept in the first law. It is a process of transferring energy into or out of a system that can be described by microscopic mechanical forces exerted from outside the system. So it's a kind of a specific transfer of energy, right? It's not just heat. Flow of heat is also a form of energy transfer. Well, work is when there is a macroscopic mechanical forces. So it's a little bit of a distinction that we should think about as well. Now, work, like I said before, need not just be mechanical, so that's a little bit of a misnomer. It can also be electrical, right? You can have a current flowing through a resistor. And we'll see, of course, examples of those as well. So I know these topics are a little bit dry and a little bit abstract. So my recommendation is kind of think about it yourself for a little bit, and really think about how these concepts might apply to your particular system that you're working on in your project. And that's really the way to gain intuition and understanding of these concepts, by really looking at specific examples. Okay, so the second law of thermodynamics, which I think I kind of went through here, is saying that the entropy of a system always increases or stays the same, this is the change in entropy as a function of time. S is entropy, delta of S is the change in function of time, is always greater than or equal to 0. So coming back here, it basically indicates something very, very fundamental. It indicates that natural processes are irreversible. In other words, if you break a coffee cup, it is basically impossible to put all the pieces back together. Now, you might say you can move time back, but the thermodynamics prevents you from doing it. And really, from a more larger scale, this is like the Big Bang, right? The universe is expanding, and that expansion is irreversible. Of course, there are theories which talk about acceleration and so on, but that's actually not true anymore. It's already proven that the expansion is accelerated. So the other outcome of the second law of thermodynamics is that temperatures tend to equalize. This is a very important concept for us, which basically means that if you have, in a closed system, if you have a hot end and a cold end, and you do nothing to this closed system, they will essentially thermally equalize. In other words, the hot end will start reducing its temperature, and the whole cold end will start increasing its temperature until they both meet and the whole system reaches a single temperature. And that's actually a very important idea, and we will use this again. So just to think about this in a more complete sense, when two initially isolated systems in separate but nearby regions of space, each in thermodynamic equilibrium with itself, but not necessarily with each other, are then allowed to interact, they will eventually reach a mutual thermodynamic equilibrium. Okay? So there are two isolated systems, but they're allowed to interact. They will reach a thermal equilibrium, a thermodynamic equilibrium. This also means that the sum of the entropies of the initially isolated systems, so if you add up the entropy of each of those systems, it will always be less than or equal to the total entropy of the final combination. Okay, let me repeat that. Can you hear me still? Okay, maybe you want to turn off the video just in case. Okay. Okay. So, is this any better, Apita? Yeah, yeah, give it a second. It's going to show up. Is it? What's happening, the sound or the? Okay. Let me try without the connector. Maybe this is better. I'll see.
Actually, this is better.
Okay. Okay.
This sounds better.
Okay. Well, let's see how it goes.
Let's just keep this instead of the earbuds.
Okay. Sounds good. Thank you. So the basic idea is that if you take the entropy of each of the individual systems and add them up, that entropy will always be greater than the it will always be less than the total entropy of the final combination. This basically shows or means that the entropy always has to increase with regard to time. Okay. Just a few, the quality here occurs just when the two original systems have all their respective intensive variables, which is temperature and pressure, as we'll see some examples. And then the final system also has the same values. So this is less important for us. This is referred to as the adiabatic condition. We'll see that later on when we talk about some examples, but for now, don't worry about it. So the conclusion here is that the entropy of a closed system always increases with time. Those are the only two big concepts in thermodynamics we really need to think about. So now let's look at some examples of heat engines and cycles. Okay. So heat engine again can be abstracted into a system that converts heat to work, and can be abstracted in a form like this, where you have a hot source at a high temperature TH, which is sending heat into the system. Okay, so that's our heat engine. Q in is the input. And this engine then does work, represented by W. But in addition to doing work, it can also lose heat to a sink at the cold part of the system, which is at a lower temperature Tc, Q out. Okay. The Carnot efficiency we saw before defines the maximum possible efficiency of a heat engine. So the heat engine, the operation of a heat engine can be represented by what's referred to as a heat engine cycle. Okay. This represents essentially a curve, generally speaking. There are many ways to represent it, just be aware of it, but most cases we represent it as a pressure volume curves. Okay, so you can see pressure on the vertical axis, volume on the horizontal axis. So let's follow what this means. First of all, the Carnot efficiency is the same as what we saw before. It's the difference in temperature between the hot and the cold divided by the temperature of the hot divided by multiplied by 100%. Okay, so this is the same equation we saw before. We'll see this again many times, so we'll not worry about it too much. So let's start here at this point of the cycle. Okay, this is a point where, let's say, the working material, which can be a gas, for instance, is at a low volume. So volume is at very low, so it's compressed, very high pressure. Okay, and it's allowed to expand. Okay, so this red curve here represents an isothermal expansion. And as we know from our example of the refrigerator, for instance, this expansion means that you are drawing heat in from the surroundings, right? You're absorbing the heat. So you're cooling the surrounding, or cooling the chamber if it's a case of a refrigerator, right? So that's that part here. And this happens at TH. It can be isothermal, it doesn't have to be. This is a specific example of an isothermal expansion when the temperature of this fluid is the same. And then there's something called an adiabatic expansion, where the temperature can change. In this case, the temperature falls. It goes from TH to TC. But really, it's also undergoing an expansion. But in this case, it's also expanding and reducing in pressure. So at this point of the cycle, you have the fluid at very large volume, right? The volume is here, but below pressure. So it's existing as a gas. Now, you can compress that gas, let's say, by isothermal compression. It doesn't need to be isothermal, so it's just an example here, at, let's say, Tc, which then reduces the volume, increases the pressure. But of course, when you compress it, the heat comes out. So that compressor, of course, generates heat, as you remember from the example of the refrigerator. Then there's an adiabatic compression, okay, which is basically energy conserving compression, and it comes back to its initial state. So if you think about the cycle, this repeats over and over again. You notice something, that it is not going back in the same cycle, right? Going down is in this curve and going back is in this curve. And the difference between these two curves is equal to the work done by the system. And this is an important concept. So the net work is the area inside the pressure volume curves. So you really want to maximize that area when you start thinking along this for these curves. Okay? And of course the work done by the system is the difference between the heat coming into the system minus heat escaping the system. Right? Assuming the internal energy of the system does not change. Of course, if the internal energy of the system changes, then you have to apply the first law of thermodynamics. Okay, so that's an example of a heat engine cycle. Here's another example of a cycle referred to as a Stirling engine. It's a little bit different. We'll see the difference, but it can also achieve the Carnot efficiency. In this case, it's also a pressure volume curve. Let's say we start at the point A, this is low volume, moderate pressure, and then you, at a fixed volume, you increase the pressure to B, so that's this straight line, and then you allow for expansion at a constant temperature. So this is an isothermal expansion, where the pressure drops, volume increases, and then there is a drop in temperature from the hot to the cold, with a consequent drop in pressure, but at the same volume, constant volume, and then there's a compression. So this compression happens isothermally as well at a fixed temperature Tc. So during these vertical lines, of course, no heat transfers. So that's why this is adiabatic, similar to the blue portions of the curve, and there's no heat going in and out. But during these expansion and compression, heat comes in or heat goes out. And the difference, of course, is the work done, which is the area under this curve. So it's just a different cycle, referred to as the Stirling cycle, and the difference is that there's this constant volume phase of it. So for our purposes, the key things to keep in mind is Carnot's theorem. Carnot's theorem states that all irreversible heat engines between two heat reservoirs, which is the hot and the cold ends, are less efficient than a Carnot engine operating between the same reservoirs. So, which means that the best efficiency that one can hope to achieve with any heat engine is given by this expression. Okay? So we can try to, let's say you're working on a solar thermal project, you can think about, okay, this is the best I can hope to do. What is my hot part, what's my cold part, and I can calculate that. Same thing with solar desalination for that matter. So there is a Carnot efficiency associated with that specific heat engine. This concept also implies that all reversible heat engines between two heat reservoirs are equally efficient with the Carnot engine operating between the reservoirs. Which means that if you have a reversible heat engine, which of course does not exist in actual nature, they are all equivalent. In other words, if you design one, theoretically, it will be basically same as any other one. This is a little bit of an abstract concept, not so important for us, but it's a consequence of the second law of thermodynamics. Let's not worry too much about it. Okay, now the last thing I would want to talk about is a specific example, and that's the last topic that I want you to understand. We'll apply what we have learned so far to look at a very simple example of a solar collector. Okay, so let's walk through this slowly. The efficiency of a solar collector can be written as, so the total efficiency is here, okay, eta is a product of the efficiency of a collector and the efficiency of the heat engine associated with that collector. So imagine there is some way to collect the sunlight and heat up the hot part, then there's a Carnot engine associated with that hot part, and there's another cold part, which gives you the total efficiency. So we need to compute all these different terms here. First we'll start with the Carnot because that's easy to compute. Right? It's 1 minus Tc over Th. Tc is the temperature of the cold part, Th is the temperature of the hot part. Area of the collector is a bit more complicated. Okay, we have to look at the absorbed heat by the collector, which could be a, let's say hot water heater with a concentrator, whatnot, minus the heat lost. This is, we'll talk primarily about radiative loss, as we said before. We'll come to that in a second. Divided by incident heat, okay, which is of course the sunlight. Now the heat lost is usually primarily radiative, so that's why there's an equal greater than sign here. Okay, of course it can have other loss mechanism like conduction, convection, and so on, but we'll only consider radiative losses for the moment. Where sigma Th, so it's at high temperature, so that's the Th. Sigma Th raised to 4, of course, is the Stefan-Boltzmann law, which we saw last class. Okay, sigma is the Stefan-Boltzmann constant, T raised to 4. So this is the power density that's emitted by this absorber. It is multiplied by the area of the absorber, A, which gives me, this is watts per meter squared, multiplied by meter squared gives me watts, and it has to be multiplied by something called emissivity, because different things emit at different rates or with different efficiencies. So that kind of adjusts the number a little bit. Emissivity is something which varies between 0 and 1. So very highly emissive materials have this emissivity equal to 1. For most good black bodies, this will be closer to 1. So we'll assume that's 1 for the time being. The incident, of course, is the sunlight. So first of all, there's the intensity of the sunlight, I solar, or the insolation, as we saw before. It's in watts per meter squared, multiplied by the area of either the area of the collector, okay, or the area of the collector multiplied by the concentration factor. So you might have a big collector, like a big Fresnel lens, let's say, on top of the collector, which increases your input aperture. So remember the very first lecture I mentioned the input aperture is important. This is how it becomes important. Here the area is multiplied by the geometric concentration factor. We'll see this again and again, so we'll look at specific examples. For now, just be aware of where this goes into play. This goes into play in the denominator. Okay. So we plug it all in, we get a relatively simple expression where the efficiency of the collector now is, Q absorbed minus Q lost divided by Q incident turns out to be 1 minus epsilon sigma T raised to 4 over C times I solar. So if you think about this equation for a second, epsilon is a constant, sigma is a constant. Okay, these two things are constants you don't have much control over. You don't have any control over, so let's ignore them for the time being. The temperature of the hot body is very, very important, as we expected, right? And there's a negative sign here, which means that I need to increase if I, this is very important, what happens if I increase that temperature? There's a negative sign here, the efficiency will go down, right? So this tells you, okay, I can, having a hot part of the heat engine to be hotter is good, but I'm going to increase my losses. So this will start going down. The concentration factor is also important. If I increase the concentration factor, of course, this efficiency goes up, right? Because this is in the denominator, it's a negative sign. Okay, so AC is the A times C is the collector area. So it's a concentration factor multiplied by the area of the absorber itself. The absorber itself is the area C. So the total effort, now we can put everything together into the total efficiency, which is the area of the collector multiplied by the area defined by Carnot, so which works out to be this expression. So you can see two things competing against each other. So that's the most important thing I want you to get out of all these equations. Right? Look at TH. So TH here has a negative sign, which means that it contributes in a negative fashion. In other words, when this increases, this term decreases. Now here TH is in the denominator with the negative sign, which means that if TH increases here, this whole thing increases. And we know from Carnot that if I increase the temperature of the hot body, my efficiency goes up. So those are the two competing things that happen in these two terms. So if I multiply them together, I know that there is some optimal point. This is the most important conclusion I want you to draw. In almost all systems, there is always an optimum point of operation. And this is true for photovoltaics. This is true for your car engine. It really comes from thermodynamics. So here we can look at this equation numerically. So the examples are plotted here. So vertical axis is the efficiency, horizontal axis is the temperature of the hot source, or TH, this TH. And you can see various plots here, and those various plots correspond to different concentration factors. Okay, C. So let's look at C equal 10, so which is this black curve here. At low temperatures, of course, when TH is equal to TC, so in this case TC is 300 Kelvin, which is the room temperature, the efficiency is 0, right? Because TC and TH is equal to they are equal to each other, so 1 minus 1 is 0, so that's 0. As I increase my TH, this plot increases until it reaches a peak value around 25-26%, okay, in this example. And then as I increase TH further, it doesn't help, because I'm losing more energy because of these radiative losses, and I start going down until very high temperatures I reach 0. It's actually doing nothing, right? So that's the interesting concept I want you to keep in mind. It's important not to just to think from a Carnot perspective, but also need to understand the losses. Of course, you have another knob you can play, which is this concentration factor. So then I can increase my concentration to 50 from 10, and I get this blue curve, which means I can push the efficiency higher, my optimum efficiency higher. Okay, I can go to 100 and push this even higher, 500, 1000, 5000, and so on. When I increase the concentration, I also get a more flatter curve here, which is good because I don't need to control the hot source temperature so precisely. So lots of nice advantages. But of course, we will see this as you increase the concentration factor, the systems get more complicated, right? You need to track the sun more precisely. You're also working at much higher temperatures, which means that materials have to survive, so reliability becomes challenging. So all these trade-offs. This is why this is a very interesting engineering problem. Okay, so I want to end a little early today, but before we end, I want to show 2 examples of solar thermal plants which actually apply this whole analysis. So this analysis we did in a much more sophisticated manner is essentially applied to design these systems. So the first solar thermal plant you see on the left is what's called a Sandia dish Stirling engine. So remember the Stirling cycle we talked about? It uses something very similar to that, again with a steam. So there's a parabolic dish. In this case, it's a paraboloid, so it's a full 3D. The focus is right there, okay? And there are pipes which allow the water to be heated up, and the steam passes through the pipes and runs a turbine. Usually the turbine is off the site, but I am actually exactly not sure where it is in this diagram. The efficiency of this particular system is 30%, concentration is about 2000. So you can compare that to the curve here, concentration of 2000, so it's about this curve roughly. This is 1000, so a little higher than that. And efficiency is about 30%, so like way down here, right down here somewhere. Temperature is usually pretty high. I forget the exact number. Yeah, it's about 700 degrees Celsius. So you can kind of compare it to the theoretical numbers. It's actually quite good for the numbers here. They're relatively large installations. Primarily started at this is development at Sandia National Labs. Some of these are installed in California with about 25 kilowatt peak per dish. The other way to implement these sorts of heat systems is what's shown here, which is a solar tower, or called a power tower. This is an example from Spain, but some of you probably have seen the one outside Las Vegas. It's closer to us. These can be very giant systems, so basically a bunch of mirrors or a very large area which focuses sunlight to a specific spot. So as the sun moves, these mirrors adjust to change their focus of their reflection, and this spot fluid is heated up, and that heated fluid is used to perform work generally, in this example, it's 250 degrees Celsius steam turbine, so steam runs a turbine to create electricity. These systems can be massive, so this is 11 megawatts, but these areas are very big as well. We're talking about several miles in diameter. So, so there are two other examples I just want to give you so you have a sense for what these things look like. I know for the solar concentrator team you will go into a bit more detail, but I think it's good for all of us to look at it. And this is the last part of the class, so I'm going to speed through this.
It's incredible, and I can't believe I'm flying this plane.
Okay, so you can see the heliostats. They're called heliostats. There are basically modular mirrors. Again, you can see the pictures there, and you can see the hot part. Zoom out.
Pointing exactly the right spot. Santiago's brought along one of these miniature parabolic mirrors, which I guess is almost like a perfect scale model of your solar tower.
Yes, I mean, the tower looks like in the middle of a circle of heliostats, and every heliostat is like, yeah, taking a different angle to reflect the light on top of the tower, and then to concentrate all the energy on a single spot.
So let me try.
So the heliostat is essentially discretizing the paraboloid structure.
I mean, this must be the challenge that you're facing.
Exactly. I mean, exactly what we have to be doing. I mean, we have to be very precise in moving the heliostats in the right position to concentrate the light there.
Sunlight is reflected from each heliostat onto a central receiver at the top of the tower. Sodium and potassium nitrate salts are pumped from the cold salts tank up to the receiver, where they absorb the concentrated solar thermal energy, reaching temperatures of up to 565 degrees. The heated salts are then pumped down to the hot salts tank, where they can be stored in a molten state or used to generate electricity via the heat engine.
This is the hot molten salt tank that contains the molten salts at 565 degrees. This is like a sleep battery, but it's a thermal battery. It's not an electrical battery. In fact, the energy which is accumulated here is enough to continue operating the turbine for 15 hours at full speed.
So this is what distinguishes this place from other solar tower generators around the world. It's actually that storage.
Exactly.
Being able to store energy this way means the solar power can, for the first time, be provided 24 hours a day, not just when the sun's shining.
This is the vessel in which the water becomes steam. Inside you have water at maybe 500 degrees centigrade and already 100 bars of pressure.
This is incredible. So what Santiago's telling us is, despite how futuristic this all looks, the actual business end, where they create the electricity, is much the same as any other coal-fired or even nuclear power plant. You see, it's a steam-driven power plant. Wow. Wow. This is what I'm talking about. Now, this looks like a power station.
Okay, I'm gonna pause here, but you get an idea. This is of course closer to us, so it's good to see. So if anyone has driven by Vegas, you might have seen this, or if you fly, for instance, from Salt Lake to California, you actually fly over this. It's basically the same kind of system. There are three of them. They're very big, as you can imagine. There are three systems you can see. And you can see the mirrors are changing, right? Different parts are on the 2-axis tracking here. You see these mirrors can trap both axes. One of the problems with these sorts of systems that you will encounter, and I should point out, is wind loading. So these things are not super. They have to be very stable to wind. So there are big challenges on how do you make sure of that. It makes it expensive. So lots of interesting challenges to solve here, but very, very exciting technology. it can, in theory, produce energy at costs that are much smaller than traditional solar photovoltaics that we put on our roofs. But of course, it's centralized, so that's the trade-off. So I'm going to stop here. I'll post links to all the videos, so if anyone's interested, of course, feel free to look at it more closely. But I'm going to stop here and see if there are any questions. So let me just summarize the important part of this lecture. We're stopping a little bit early, but the important is that for thermodynamics, I want you to really understand, like I said before, how to apply the thermodynamic principles to your particular system.